Your calculations are correct. For two 25 kVA transformers, each rated at 480 volts to 240 volts, you will need a primary overcurrent protection device rated for at least 200 amps. Here's a breakdown of the calculations. Firstly, calculate the total kVA amps, which is 25 kVA amps times 2 equals 50 kVA amps. Secondly, convert the total kVA amps to volt amps. This is done by multiplying the kVA amps by 1000, so 50 kVA amps becomes 50,000 volt amps. Thirdly, identify the primary voltage, which is given as 480 volts line to line. Fourthly, calculate the primary current using the formula total volt amps divided by the product of the primary voltage and the square root of 3, which is approximately 1.732. Plugging in the values, we have 50,000 volt amps divided by the product of 480 volts and 1.732, resulting in 180.41 amps. This means that each transformer will draw approximately 90.21 amps from the 480 volt source. To provide sufficient capacity for both transformers, you will need an overcurrent protection device rated for at least 200 amps. It's important to note that the calculations above do not take into account the power factor of the transformers. If the power factor is less than 1, the actual current draw will be higher than the calculated value. However, for most applications, a power factor of 0.8 to 0.9 is typical, so the calculated value of 200 amps should be sufficient. Once the transformers arrive, you can verify the actual current draw and adjust the overcurrent protection device as necessary. When selecting an overcurrent protection device, it is important to consider several factors, including the transformer's inrush current, the ambient temperature, and the altitude. Transformer inrush current is the high instantaneous current that flows when a transformer is first energized. This current can be several times the transformer's normal operating current and can cause nuisance tripping of the overcurrent protection device. To avoid nuisance tripping, it is important to select an overcurrent protection device that is designed to withstand the transformer's inrush current. This can be achieved by selecting a slow-blow fuse or a circuit breaker with an instantaneous trip setting that is above the transformer's inrush current. Ambient temperature can also affect the performance of overcurrent protection devices. Overcurrent protection devices are typically rated for a specific ambient temperature range, and if the ambient temperature exceeds this range, the device may not operate properly. In high ambient temperature environments, it may be necessary to select an overcurrent protection device with a higher current rating or to provide additional cooling for the device. Altitude can also affect the performance of overcurrent protection devices. At high altitudes, the air is thinner, which can reduce the cooling capacity of the overcurrent protection device. In higher altitude environments, it may be necessary to select an overcurrent protection device with a higher current rating or to provide additional cooling for the device. In addition to the factors mentioned above, it is also important to consider the National Electrical Code requirements for overcurrent protection of transformers. The National Electrical Code provides specific requirements for the size and type of overcurrent protection devices that must be used to protect transformers. It is important to consult the National Electrical Code to ensure that the overcurrent protection device selected meets all applicable requirements. The National Electrical Code Section 450 covers transformers. Specifically, 450.3 addresses overcurrent protection. For transformers over 600 volts, the primary overcurrent protection is typically limited to 300% of the transformer's rated primary current if using a circuit breaker, or 300% if using fuses. For transformers 600 volts or less, the primary overcurrent protection is typically limited to 125% of the transformer's rated primary current if the primary current is less than 9 amps. If the primary current is 9 amps or more, the overcurrent protection can be up to 250% of the rated primary current. These percentages can be found in NEC Table 450.3b. The secondary overcurrent protection is also important and is usually limited to 125% of the secondary current rating. This protects the secondary conductors and connected equipment from overloads and short circuits. When determining the appropriate size of the overcurrent protection, you must consider both the primary and secondary currents and comply with the NEC guidelines. Remember, the goal is to protect the transformer and the connected circuits from damage due to overloads or faults while allowing for the transformer's normal operating characteristics, including inrush current. The selection of the overcurrent protection device should also consider the interrupting rating. The interrupting rating is the maximum fault current that the overcurrent protection device can safely interrupt. It is important to select an overcurrent protection device with an interrupting rating that is greater than the available fault current at the transformer location. This will ensure that the overcurrent protection device can safely interrupt a fault and prevent damage to the transformer and connected equipment. To determine the available fault current, a short circuit study may need to be performed. This study will calculate the maximum fault current that can flow at various points in the electrical system. The short circuit study should take into account the impedance of the utility transformer, the conductors, and other electrical equipment in the system. Once the available fault current is known, an overcurrent protection device with a suitable interrupting rating can be selected. Furthermore, the type of overcurrent protection device should be considered. Fuses and circuit breakers are the two most common types of overcurrent protection devices. Fuses are single-use devices that must be replaced after they have interrupted a fault. Circuit breakers are reusable devices that can be reset after they have interrupted a fault. Fuses are typically less expensive than circuit breakers, but they may not be suitable for all applications. Circuit breakers offer more flexibility and control, and they can be remotely operated and monitored. When selecting an overcurrent protection device, it is important to consider the specific application requirements and the advantages and disadvantages of each type of device. In summary, calculating the primary overcurrent protection for transformers involves several steps. Firstly, determine the transformer's kVA rating and primary voltage. Secondly, calculate the primary current using the formula voltamps divided by the product of the primary voltage and 1.732 for three-phase systems. Thirdly, consider the transformer's power factor, inrush current, ambient temperature, and altitude. Fourthly, consult the National Electrical Code for specific requirements and limitations. Fifthly, select an overcurrent protection device with an appropriate current rating and interrupting rating. By following these steps, you can ensure that the transformers are properly protected from overloads and short circuits. Remember to always consult with a qualified electrical engineer or electrician when designing and installing electrical systems. They can provide valuable expertise and ensure that the system meets all applicable codes and standards. Consider the application of the transformer. For example, if the transformer is feeding a critical load, such as a hospital or data center, it may be necessary to provide redundant overcurrent protection. Redundant overcurrent protection involves installing two or more overcurrent protection devices in parallel, so that if one device fails, the other device will still protect the transformer. Also, consider the coordination of the overcurrent protection devices. Overcurrent protection coordination is the process of selecting and setting overcurrent protection devices so that they operate in a coordinated manner. The goal of overcurrent protection coordination is to ensure that the overcurrent protection device closest to the fault will trip first, minimizing the impact of the fault on the rest of the electrical system. The overcurrent protection coordination study typically involves calculating the time current curves for all of the overcurrent protection devices in the system. The time current curve shows the amount of time that an overcurrent protection device will take to trip at different current levels. By comparing the time current curves of different overcurrent protection devices, it is possible to determine which device will trip first for a given fault current. In general, the overcurrent protection device closest to the fault should have the fastest time current curve. Finally, consider the future needs of the electrical system. If the electrical system is likely to expand in the future, it may be necessary to select overcurrent protection devices with higher current ratings. This will allow the system to be expanded without having to replace the overcurrent protection devices.